On to the last parts of the kidney. So kidney damage. What would be causing kidney damage and what would then lead to kidney failure? And there's actually 4 stages of disease. So you might have mild damage, in which could be stage 1 up to stage 4, where it's very serious and your kidneys aren't working at all. So what would cause it? How could it be diagnosed and how could it be treated? And where would it be happening within the kidney? Just stop and think about those questions for a moment. So the first question, where would the kidney damage be happening? There are many different parts that we've had a look at in the kidney, but the part where we've got filtration going on, this is going to be one of the fundamental parts. And if we get damage to this filter and the ultrafiltration process, then we will get things going through that should not go through. So we could get, if there's damage and now the holes are too big, we could get red blood cells going through, and this would lead to blood in the urine. And so yeah, blood in the urine is usually a fairly serious thing. It could be caused by an impact. You could, for instance, boxers get punched in the kidneys and then it leads to blood, and that might be okay, it might just repair, but it could also be a sign that you have kidney damage. So what's this part? Well, this is the part that's being damaged. There is the glomerulus, and the glomerulus is surrounded by Bowman's capsule. So if those bits are becoming damaged, then we will get things that we shouldn't get going through. And the other thing that would be proteins. We'd get proteins going through. Now, if you've got kidney damage as well, it could be damaging the other parts to do with reabsorption. And we might not get enough reabsorption and excretion of the right things. We might have, if the kidneys are failing, we might have too much urea still circulating in the blood. So an increase in urea would also be a sign that your kidneys are failing. And it might not be regulating your salt level correctly. So we could say that it's when kidneys no longer effectively filter the blood. And other things that could lead to this, well, we could have cancer, but one of them could be diabetes, which leads to high blood pressure. So it could either be high blood pressure which isn't associated with diabetes, or it could be the high blood pressure and the diabetes leading to higher glucose concentrations, and that would cause higher pressure. So we'd have more, if we're thinking about where this is happening, we'd have more force on the glomerulus. And so that region would be down here. We'd have too much pressure pushing out, and this could lead to damage to the glomerulus, and then we would have more things seeping through into the filtrate and making their way into the filtrate, like red blood cells and large blood proteins. Now, if they're not working well either, we talked about an increase in urea. And so actually we can use urinalysis, which is analysing urine, to diagnose different diseases. If there are red blood cells there, it could be indicating damage to the kidneys or something else causing blood to flow into the filtrate, like cancer. If there are white blood cells there, it could be that it's an indicator of infection, so urine infection, causing white blood cells to be there. If there are large blood proteins, then it means, yeah, there's something going wrong with ultrafiltration, and it could be the start of kidney disease. And so we can see all of those in a blood test. We can look at those different markers, and doctors can use it to diagnose what's happening. So here we have some of the things that they could be looking at, and this is a kind of a urine test chart, and they might have, through doing it, they can have colour changes, and they can monitor different things like our white blood cells, the leukocytes. They could be looking at nitrite. They could look at the proteins that we talked about, because if the large proteins are getting through what should be small gaps, then that indicates a problem. The pH of the blood, whether there are ketones, whether you've got too much bilirubin. So bilirubin could be an indicator of liver function, and whether you've got glucose. Now, if you've got glucose in your blood, then that is an indicator that you have diabetes, because there's so much glucose, too much glucose going through, and with so much glucose passing in, if there's too much, then not all of it could be reabsorbed in the proximal convoluted tubule. And if there isn't enough absorption, then that's going to end up in the urine. Okay, so urinalysis can be used to diagnose a lot of things. And here's our quick summary. So if we've got blood or proteins, it indicates damage to the kidneys. It could indicate kidney disease, which could have been being caused by high blood pressure or potentially diabetes, or both at the same time. Or it could be cancer. It could be an impact to the kidneys. And the damage mainly is in the glomerulus if we're talking about filtration. But kidney disease can also mean not effectively filtering out, so too much reabsorption of urea. So yeah, we could get blood cells and large proteins, and they would be present in the urine. And if we get glucose in the urine, then that's an indicator of diabetes. Okay, and so how it's treated really depends on how serious it is. So my father-in-law has stage 3, and there's actually very little they're doing. They might have changed a few of the drugs that he's taking for his other conditions, but they don't actually do much. And so that means if you've got kidney disease, we talked about having too much urea in your blood, and that can lead to neurological problems. So he often feels tired and sometimes a bit confused and other things like that. But until you get to stage 4, then not much is done. So when you're at stage 4, that means almost complete failure of the kidneys, and they're really not filtering very much. And so then there's 2 options. The first one is dialysis. And in dialysis, the blood flows out of the body through a pump, and then it goes through a dialyzer. And you can see that there are fluids that are put in to the dialyzer. And then the blood returns back to the body and is pumped in. So what's happening in the dialyzer? How is this machine taking the place of the kidneys? Because the main thing was that we wanted to get rid of urea, get rid of excess water, make sure that glucose was at the right level, and salts were at the right level as well. So we want to regulate those things. So how does pumping it through this machine achieve that? Okay, well, it achieves it by, over here in the dialyzer, we get the blood to flow through, and it's flowing through in an opposite direction. So we get the counter current, we get to maintain gradient. So if the blood is flowing through here, now if the blood has got too much glucose, or if it's got too much urea, in a kidney patient, it'll definitely have too much urea because their kidney's not working to get rid of the urea. Then the fluid on the other side is the dialysis fluid. And this fluid has no urea, and it has the correct concentrations of salt and sugar. So it's the correct concentration for filtered blood, like it would come out of a healthy kidney. Now let's think about what's going to happen here then. So just by running the blood close to each other with this special partially permeable membrane, the Visking tubing, or dialysis tubing, by running them close to each other, we can just make use of a gradient. So if there's too much glucose, well, it would in the blood, it would diffuse out. If there was not enough glucose, then this side we've got the correct concentration in the dialysis fluid and it would diffuse down the gradient. Now here with urea, if there's no urea, then almost all of the urea is going to pass out of the blood into the dialysis fluid, which is being pumped around. And so by the time the blood comes out, it has now been rebalanced. And so the other thing that would be happening is the same thing with salts and, which could be sodium Na+, it could be the chloride ions, and it's also the pH of the blood, so H+ ions. And these are all just going to diffuse down until the blood is meeting the same concentration as the dialysis fluid. And then when it goes back into the body, it's cleaned. And so dialysis is a big thing. People have to go in, depending on how severe it is, maybe up to 3-4 times a week, and they go and have dialysis. Of course, the other solution is that you get a new kidney. So depending on your age and the availability of organs, you could have a kidney transplant. So new kidney transplanted in. Now actually we only need one kidney. So this is where you hear of people donating kidneys to people in their family. Or they come from organ donation and we can replace the kidney. And then that one kidney is enough and you can function on one kidney. So here's a quick recap. So we use hemodialysis or dialysis to treat kidney disease. The patient's blood is flowing through tubes next to the dialysis fluid, but it's separated by the semi-permeable membrane, which is, we said, was dialysis or Vissking tubing. And the fluid, the dialysis fluid, has the same concentrations as normal. We could think of it as being clean or filtered blood. And it's going to have no urea. So anything that's in excess, like urea or salts or glucose, diffuses down its concentration gradient, and therefore it returns all of these to the normal level. So it's doing homeostasis outside. And that was Ava, my 3-year-old daughter. All right, so on to the outline, the role of the Malpighian tubule systems in insects. So the IB have chucked this in as a bit of extra stuff to think about other organisms and how they deal with their waste. So let's have a look what's happening here. Well, around the outside, they don't have blood. So weirdly, they have something called hemolymph, which we can spell like that as well. Hemolymph, it's a bit like tissue fluid, which surrounds our cells. It just doesn't pool, they don't have something that pulls back into blood. So they've got lots of cells, and all these cells are creating waste, which they need to get rid of. And they're going to be breaking down proteins. They are going to be removing the amine group, and then they need a way to get rid of that. And this causes the formation of uric acid. And they also need to get rid of excess salts, so that's going to go into this fluid, and excess water needs to go in. And so this is all connected. It's almost like their kidney is part of their gut. So they don't really have a kidney, but they've got these tubules. And these tubules join, so they would be putting food in here. This is the midgut, and food is going to flow down, and they're going to get rid of their feces, the stuff that they can't digest. Because a lot of insects are carnivorous, and they're certainly eating other things, even if they're herbivores. And so it's going down. And so they kind of use their gut as their kidney with these Malpighian tubules. So they use Malpighian tubules. They then put the excess salt, so Na+ would be going in there. They put the excess uric acid, so uric acid ends up in here as well, and excess water. And as it moves down, they then have their version of selective reabsorption. So we saw that in the proximal convoluted tubule, and here they're going to reabsorb the water and the salt. And so this is active transport. So they're going to actively transport the salt out, and the water will follow. And it's also over here we've got active transport of salt into the tubules as well, and that is what draws water in. So water will get drawn in. So we saw this kind of principle before, where if we put salts, we saw it with bile pigments which have salt, and that draws water into the ducts in the liver. So where we have salt, the water will follow. And so by actively pumping salt in, we will get water following it. And then it will help the flow down. And then we can actively pump salt out, and that will help us reabsorb the water. And so what they excrete is uric acid crystals, which is kind of it's a more concentrated form. And that means they do have a reduction in water loss. It helps them lose a bit less water. Okay, so this is a rather long essay. I don't think they would ask you about it in this much detail, but yeah, they need to do their own homeostasis. Insects need to keep hemolymph within a certain range. They form uric acid from the breakdown of proteins and amino acids, and it gets transported into Malpighian tubules, and that's going to reduce the concentration of uric acid. It branches off into the gut, and we then get sodium and potassium actively transported into the Malpighian tubules. Then water will be absorbed because water is going to follow into the tubules. And then later on, these ions are actively, or selectively, we could say as well, actively reabsorbed. It's active transport. And then we're going to get water reabsorbed as well, because again, where salt goes, the water will follow. And then eventually they get this uric acid paste being formed, and it's excreted, and that's going to help them maintain their concentration of hemolymph. And that is it.